Number 27. A bus contains a 1,500 kilogram flywheel, a disc that has a 0.6 meter radius and has a total mass of 10,000 kilograms. Letter A. Calculate the angular velocity the flywheel must have to contain enough energy to take the bus from rest to a speed of 20 meters per second, assuming 90% of the rotational kinetic energy can be transformed into translational energy. All right. So there's a lot of information given to us in the first part, right? So what you want to do anytime you're presented with conditions where there's a whole bunch of numbers and concepts coming at you, you want to try to boil it down to, or take a piece of what was given and try to find the most essential part. All right. Now, given all the information, the most essential part of what we need to start with is this particular concept, that energy is being transformed. It's this word right here that is key. So when energy is being transformed, right, it means that energy is being converted from one form into another. And we also know that conservation of energy is always present, that energy is always conserved. Okay? So in this particular problem, then, what I'd like to start with for letter A is I'd like to start with the general conservation of energy formula that says that the initial energy that's inherent in a system has to equal the final energy that's inherent within that system. Now, in terms of this problem, what are the energies that are present? Well, they told me two types, right? They said that there's some rotational kinetic energy that's present, and then it's being transformed into this translational energy. Translational energy, I mean, the word translational is just it's a fancy word for linear. All right, so if you think of linear energy or energy of motion, you're thinking, kinetic energy, right? 1/2 mv squared. So that's basically the two types. So what I'm going to do here is I'm going to break each of these up into their corresponding energy values. So here we'll have the kinetic energy of rotation initially, plus then the kinetic energy of translation, or I should say translational kinetic energy. I'm just going to write kinetic energy of motion. This is the 1/2 mv squared. Equals then the kinetic energy of then rotation finally, right? Plus then the kinetic energy of motion finally. And I forgot the little f and that f. Oh, well, just seeing if you're paying attention, that's an I. Okay, so now we have this particular formula, all right? Now it says assuming 90% of the rotational kinetic energy can be transformed. All right, so this problem sometimes gives students trouble. How do we deal with the 90%? Do we divide? Do we multiply by it? Do we have to subtract it from 1? Right? How do we, or from 100%? I was just thinking about if you convert it into a decimal. How do we treat it? So the way we treat it is you can think of it logically. All right. So let's pretend we don't know what the kinetic energy of rotation is initially, but we know whatever we have initially in the problem will represent 100% of what we have. Okay. What we have is what we have. So in other words, I could take then 100%, multiply it by my kinetic energy of rotation initially, right? Because 100% times whatever I had initially is just itself, right? Remember, when you actually do multiplications with percents, it's just a 1 when you would convert it to a decimal, okay? Right, so if you had $100 and then I told you you had all 100% of those $100, you'd say, oh, I have $100, right? So this is just the same. This is the same value. The reason why is because this would be, we would convert that, like I said, to a decimal, which would be 1 multiplied by KE R sub I. Then this term, initially, it says it starts at rest. So therefore, this is 0. Okay, so that term kind of just drops out. So this is plus, I'm actually just going to leave out the 0 there. So now the final value. Now remember, it goes back and it says assuming 90% of rotational kinetic energy can be transformed. Okay? Pretend instead of they're talking about energy, pretend they're talking about money. And you have $100 and 90% of those $100 are going to be transformed into somebody else's bank account, or I should say transferred, right? Transferred, tomato. So if I told you have $100 and 90% of those $100 are going to be transferred into somebody else's account, how much do you have left? You tell me easily, right? $100, right? So what I'm going to do then here is I know that whatever I started with, I have to then multiply it by 10%, okay, or 0.1. right? This would be the decimal form of 10%, KERF. Now you could have, instead of written in here, you could have written 1 minus 0.9. That's obviously 0.1. So this is how you would have come to the value of 0.1. I'm just going to leave it as though 0.1 for now. And then plus some kinetic energy value of motion finally. Okay? So what do we do now from here? Well, I realize that these two values, right? Actually, what I should have done here, because these two values will be different. So what I should have done was I should have written in, so my substitution here, this is the final value, okay? Now, I realize that I'm taking away 90% of the initial value, okay? So therefore, 10% of the initial value will be left. So really what I should have in here is the sub I value, okay? So 10% of whatever I had initially will be left finally. So this term is equivalent to this term. Hopefully that makes sense, okay? Now I realize that I have these two variables that are the same. So, right, I can combine them. I can subtract the 0.1 KE R sub I from the right-hand side and then do the same thing over here. 0.1 times KE R sub I. And lo and behold, look what we get. So we get here a value of 0.9 times KE R sub I is equal to then the kinetic energy of motion finally, KE MF. So this is really the important equation, okay? So really this 90%, you're treating it in the context of you're going to take 90% of the initial value and convert that into kinetic energy of motion in the final state. And that should kind of make sense, right? The kinetic energy of motion in the final state should be 90% of whatever you started with in terms of your kinetic energy. Now you might say, why'd you go through this whole rigmarole? That seems pretty straightforward. It may to you, but it might not to somebody else. So, yeah, that's why. Now, what I'm going to do here is I'm just going to simplify everything, okay? I'm going to erase over here, all right? And I'm just going to bring this value on up. 1 second. Okay, just so I have a little more space. So here is now our formula. So now what I'm going to start doing is plugging in some variables, right? My kinetic energy of rotational motion is right here in terms of its formula. It's 1/2 I omega squared. Okay, so now it's 0.9 times 1/2 I omega squared. And this is the initial, all right, is equal to then, and we don't even really need the value of initial. I mean, that's the only omega in the problem. And then this will equal then the kinetic energy of motion. So this is 1/2 mvf squared. Okay? Now what we need to do, remember the whole goal is to find, what is it asking us? Calculate the angular velocity. Oh, look at this. Here it is. There's the variable. This is, oops, this is what I'm after. Right there. Okay? So in order for me to calculate this, I got to know everything else. So, and we actually do, okay? We do know well, we don't at the moment. We can easily solve for it, though. We need to know the moment of inertia for the system. And they told us it's a disk. All right, the flywheel is a disk that has a certain radius and a certain mass. Oh, right, that's all we need for the moment of inertia for the disk. All right, mr squared over 2. So what I'm going to do here is I'm going to do this substitution in a little bit, but I'm just now going to solve for w sub I. All right, so in this context, what I'm going to do here is just divide out the 0.9, the 1/2, and the I on over to the right-hand side. Okay? You know, a little trick here, what you can think about, how you can do this is just, if I were to create like two fractions here, obviously put them over 1, they're the same thing. What you're allowed to do is you're allowed to move, as long as these terms in here are multiplied together, you're basically just, this is like a cross multiplication. You can take this value and just bring it on down, right? You can just go across the page like that. Similarly with any value over here, you can bring, if you wanted to, I don't know, for some reason, bring the VF squared somewhere, you can bring it down to here. These are the only two places you're allowed to move it. All right? I mean, that's a little shortcut there. Okay. So now let's erase all this. And I already mentioned what we're going to do. So here's the WI squared is going to be equal to now, it's 1/2 MVF squared divided by now 0.9 times 1/2 times then I. Okay, notice the 1/2s will cancel, right? 1/2 divided by 1/2 is itself. And now I'm going to substitute in my equation for moment of inertia for I. And also, I need to also take the square root, right? Because I want omega, not omega squared. So I got to take the square root of both sides here. So this will get me now my final equation. So omega will be equal to square root of mvf squared, all divided by 0.9 times now I, which is the mass. Okay, now we just got to be careful here. Actually, one second, guys. Let me just go back. I want to give myself a little more space if I can. Hold on. Probably just move this up a slight bit. Okay, so here we go. So square root, this is the mass. Now it's very important. I really should have detailed, what the mass is. Now remember, this is for translational energy. So it's the mass of the truck. Okay, that's what's important here. Not the mass of the flywheel. You got two masses in the problem: mass of the flywheel and mass of the truck. So what you need to take into account when you're talking about translational motion is the mass of the object that is moving linearly, and the truck is the object that is moving linearly. So this is the mass of the truck multiplied by the final velocity squared, all divided then by 0.9, now multiplied by this formula. This is the I. mr squared over 2. Now m stands for mass, but mass of what? Well, mass of the body that's rotating. What's rotating in the problem? It's the flywheel. So it's this mass that is important. So I'm going to write mass of the flywheel, so m sub f for flywheel, multiplied by the radius squared. There's only one radius, so that should be apparent. Divide that baby by 2. So now here's our value, okay? So now all we have to do is plug in the numbers. So the mass of the truck was 10,000 kilograms. The final velocity they told us of the truck, it had to obtain 20 meters per second. That's squared, then divided by 0.9 times then the mass of the flywheel, which was the 1,500, multiplied by its radius of 0.6 meters. And that's squared, all divided by 2. All we got to do is plug this into the calculator now. So let's do that. I'm going to just do the denominator first. So 0.9 times 1,500 times 0.6 squared divided by 2. 243. Now I'm going to do the numerator. 10,000 times 20 squared, and then divide it by that denominator value, and then take the square root. So I get about 128.3. So it looks like 3 sig figs should be appropriate. So this is 128 radians per second. Why is it radians per second? Because I'm solving for angular velocity, and those are the units of angular velocity. All right, so that takes care of then letter A. Now letter B. It says how high, how high a hill can the bus climb with this stored energy and still have a speed of 3 meters per second at the top of the hill? All right, so let's draw just a quick little picture. Here is our hill. Let's pretend the truck is down here, okay? And it's going to have now a certain amount of stored energy in it, all right? Now, there's a couple of ways you might interpret this problem. It's a little ambiguous when they say this stored energy. I don't, this is open to interpretation. You got to figure out, critically in terms of reading comp, what exactly they're talking about. In my opinion, it's a little confusing, but I believe what they're trying to get at is the stored energy that is inherent in the flywheel, okay? So stored energy, all right, of the flywheel. Okay, and that's really all that they're referring to. So now, when we think about this in terms of the energy then that is inherent in this truck initially, it's going to be, all the energy is going to be found in the flywheel. Okay, so I know that my kinetic energy, I could have just written energy initially, right? But it'll be a kinetic energy of rotation initially. We know that the initial conditions will be found by using this particular formula. Okay, it's 1/2 times I times omega squared. Now we calculated omega over here, right? And we know what I is because we had to calculate it over here. And then we can just take that and multiply it by 1/2. So what I'm going to do is I'm actually going to do that math up here. So this is just 1/2 multiplied then by the moment of inertia for the flywheel, which is right over here, guys. It's right down here on the bottom. I'm circling it right now. All right. Just plug that into the calculator. Let's see if we get a nice value. So it's 1500 times 0.6 squared divided by 2. We get exactly 270. So I'm just going to leave it as 270 for now, okay? Because it's an exact value. And then that will then be multiplied by our omega, right? Which is what we found was the 128. It was like 0.3 or so squared, okay? This is all the energy that's inherent initially, okay? Now, the truck is going to make its way on up the hill, all right? And it's eventually going to now have a final kinetic energy, okay? That is, so they're telling us that the kinetic energy at the end, or finally, that the bus will have a speed of 3 meters per second. Okay, so I know then that this final kinetic energy must be 1/2 multiplied then by the mass of the bus, because that's the mass that's necessary to be used when you calculate translational energy. So that's going to be multiplied by 10,000. Then multiply that by 3 meters per second, and that's squared. Now what we're assuming is we are assuming that this initial energy, okay, this is the only initial energy that is inherent in the system. Okay? They're asking us how high, okay, so if I were to dot, I'll just actually dot it this way. I mean, not that I was going to draw a little triangle, but I don't need to. So how high of a hill? This is H. Okay, that's what they're asking. How high of a hill can this truck climb? If this stored energy, meaning the energy that is inherent in the rotating flywheel, is converted, if all of this energy, actually I shouldn't say all, because we have to also keep this assumption in play that only 90% is transformed. So 90% of this energy is transformed into kinetic energy finally, because it's moving at the end, 3 meters per second, and it will also be converted into this potential energy. All right? So remember that 90% of this initial will be converted into kinetic energy and potential energy at the end. So writing this now on out, what I can now write is I'm going to say, again, energy initially will equal the energy finally. Now 90% of what is present initially will be converted into the final values. That's what I just discussed. So I can say now 0.9 times, and I already explained why that comes about. So 0.9 times the kinetic energy of rotation that's present initially will be converted into kinetic energy finally, plus then potential energy finally. Now we already know what the values are for the kinetic energy of rotation initially and the kinetic energy of translation finally. Okay, it's just these numbers. So what I'm going to do here is I'm going to plug this number in to my calculator because I don't have a lot of room here. All right, you'd want to solve the exact value. But what I'm going to do is I'm going to take 270 multiplied by 0.5 and then multiply it by 128.3. So here we get a value. So this is now going to be 0.9 multiplied by 2.22 or so times 10 raised to the, what do we got here? 3, 4, 5, 6. It looks like 6. That will then equal the final kinetic energy, which is, again, I'm just going to take that value, 0.5 times 10,000 times n3 squared. So this is 45,000. So 45,000. And add to that then the potential energy finally. Now the potential energy, remember the formula, PE is equal to mgh. The mass of the truck is the mass that is important here in terms of its potential energy. Multiplied by gravity, then multiplied by the height. So what I'm going to do here is I'm going to write it on out, PE, because I don't have a lot of room over here. So the mass of the truck was 10,000. Multiply that by 9.8, and that obviously will become 98,000 times then your H value. Okay, so this is 98,000 H. Okay, now look, this is one equation with one variable. Let's just solve it, okay? So let's take our answer before, the 2.22 times 10 to the 6th, multiply by 0.9, subtract then the 45,000, and then what you're left with would be a division. You divide out then the 98,000. It looks like we get exactly, so H is then equal to 19.9 meters. All right, and that would be the final, that would be the total height that this bus can reach. All right, so this one was a little tricky. There's a lot going on, a couple of assumptions that have to be made in terms of what exactly are they talking about in terms of stored energy and so on and so forth, okay? But, you know, hopefully it makes sense. And I appreciate you guys watching. Thank you very much. Please remember to subscribe. Easy way to help us out. Hit that like button too and tell your friends. All right, we appreciate it very much, and we look forward to helping you with the next problem. Take care.